Now that we know the register and memory differences between traditional computer architecture and embedded systems, let's talk about the last topic in this section of the course, branches. Branches are significant sources of loss of performance. Since pipelines need to fetch brand new instructions whose locations are unknown, and their scheduling and evaluation poses significant overheads and affects the design. We know that branches can have a great effect on the efficiency of execution of a program. Imagine the effect of branches on VLRW architecture for a minute. One wrong move and you may have to throw away not one but multiple instructions, and all the gains that you had could be compromised. So students, the last aspect of microarchitectures that is really important for embedded systems in particular is branches. As you know, branches are very frequent in many programs. In fact, it is said that every 10th instruction is a branch, typically. So we are going to test our knowledge of branches through a simple quiz. What I'm asking you to do here is to list the different types of branches found in programs. There are 4 of those. Please go ahead and write your answers now. So the first kind of branches that we see here are conditional branches. As you know, many programming constructs such as if then else and while loops, for loops, all these kinds of conditional constructs generate these type of branches. The control flow goes in one direction on the branch being true and goes in other direction on the branch being false. The second type of branches are unconditional branches. Remember all those loops? When the loop is done in terms of its body, again it has to go and do the next iteration, and so there is an unconditional branch from the end of the loop body to the beginning of the loop body. And almost all the loops, for loops, while loops, repeat until loops, have these unconditional branches. The third type of branches, and this may be less apparent, are all those function calls. Remember what happens when a function call takes place? We are at a particular place in the code and we want to go to that location which has the body of the function call. And so typically this type of an instruction is called as branch and link. So what this instruction does is it transfers the control flow to the beginning of the function call body, and it also causes something called as link, which pushes the parameters on the stack and so on. This is one of the most important types of branches, and it does something much more than just transferring the control from one place to the other. And the last type of branch, which may not be that easy to again appreciate, are called as indirect branches or indirect jumps. Remember all those case statements and switch statements? Many times you go to a particular table in such cases, and from there you carry out another jump. And that's why these types of branches are two-level, or what are called as indirect branches. Many times a branch jumps to an unknown offset from a given location. That offset is typically computed in a register, and using the value of the offset and the current PC address, the branch goes to that location. And again, this is an example of an indirect branch that takes place on the content of register. Now let us recall what is the problem with the branches. Branches are of course great for implementing control flow. They allow the program to execute in different ways on different inputs. But what happens during the execution of the branches, as you can see through this simple pipeline example, is that it results in a bubble. In other words, each of these instructions is going through multiple stages. Typically, the instruction is fetched, then it is decoded, then it is executed, and then we have a write back. So what happens to branches given these different stages of execution? If the instruction is a branch, after the decode stage, you can see that many times we know its outcome and target, and that is too late to fetch the next instruction to be readied for execution. And due to these, a bubble is caused. In other words, it takes few more cycles once we know the outcome of the branch and its target to get the destination of the branch, or the instruction at the destination of the branch. And such things lead to delay in execution. In other words, branches break the execution pipeline, and those delays can lead to significant loss of cycles, especially since every 10th instruction is a branch. So given what we saw on the last slide, what are the ways to mitigate these delays? One possibility is to fill them up with the useful instructions which could execute, but that would mean that the branches need to be moved around, and there are limits to such optimizations. So we are going to look at two important ways of dealing with these problems of the branches. First way to deal with the branches is anticipate. That is, we are going to see that, oh, this branch is going to go in this particular direction, and therefore I'm going to go ahead and execute those instructions in anticipation. That way of execution is called as speculation. The second way of dealing with branches is to entirely remove them, converting the control flow into what is called as a data flow. So what is the idea here? The idea is, consider a branch that has two outcomes, true and false. On one outcome, one set of instruction executes. On another outcome, another set of instruction executes. Now consider executing both of these instructions. And finally, when we know the branch outcome, we are going to pick one of the instruction streams and commit their results. So if we do this type of stuff, then it is called as predication. So what is predication? Predication is executing both sides of the branch and keeping the results ready, but not committing them. When the branch outcome is known, take that part of the branch and take its results and commit it to the destination. What is committing a result means? Committing means write back. We can write back the result into a register, or we can write it back into the memory depending on the kind of instruction it is. For example, if two registers are being added and the result is being stored into a third register, upon the branch outcome being known, we'll go ahead and write the result into the destination register. However, if it is a store instruction, we will, upon knowing the branch outcome, again take the result of the store and go ahead and put it in the memory location. Now consider these speculative execution in VLIWs, which is our favorite embedded architecture that we have been discussing. The real question here is, if we speculate and go in a particular direction and start executing those instructions, then what happens on misprediction? What is misprediction? That means we have chosen a wrong direction to speculate upon. In such a case of misspeculation, we have to throw away a whole lot of results, and the instructions that are executed have to be discarded. Not only we will waste a lot of cycles, we'll also waste a lot of power or energy here. This idea of speculation is great in superscalars, but it is not good in VLIWs and embedded systems, especially because of the energy consumption that is incurred upon misspeculation. And that brings us to yet another concept which is really important and which is followed in VLIWs of what is called as unbundling of the branches. Let us take a look at the important concept of unbundling. Typically, in a branch, there are three things which are involved. First is compute the branch condition. Second is compute the target of the branch, or where the branch is going to go in terms of the PC address. And third is combine the two and actually implement the jump to take the transfer of control to the target. So a typical VLIW implementation undertakes unbundling of three different components of the branch. It separates the where part and first detects or determines the target where the branch instruction is going to take us and starts preparing the instruction stream in terms of the fetch. Next, it determines whether that instruction stream will be selected for the target by determining the branch condition. For example, if the instruction is evaluated into true part, then one stream is fetched. If it is evaluated into false, another stream is fetched. And that decision in terms of whether the instruction is true or false is made next. And finally, the third component is all about the instruction's execution, knowing the instruction stream to go for and the condition. The next decision is when to actually take that jump. And that's the third part of it. As you can see here, the first part is readily evaluatable at an earlier point because the branch targets are typically known well ahead of time of the instruction's execution. Then the whether part is typically evaluated, deciding on the condition. And finally, down in the instruction stream is when the actual jump is carried out. So what is the advantage of breaking these three components into separate parts? We can adjust these fetching of the target instructions and prepare the instruction streams and so on in advance, minimizing those bubbles. Typically, the unbundling of branches in VLIW occurs in one of the two ways. The first way we are going to look at is called as two-step branching. In this solution, we separate the outcome of the branch or the comparison part of the branch from the branch instruction itself. In other words, we compute the predicate of the branch and hold the comparison result in what is called as a branch condition register. The comparison part is typically evaluated earlier, and then the actual body of the branch, which has the branch target and the jump itself, follows. The delay between the compare and the branch itself can be filled with some useful operations. This allows the branch to be broken into two pieces, and we can start the evaluation of the branch earlier at the point of comparison, then fill it up with the useful instructions, and then finally can take the branch when we hit the branch instruction itself. Let us look at an example to illustrate the two-step branching. In the original VLIW instruction, when the branch target and the jump itself were all combined together, there were 5 delay slots. In other words, after we decide to take the branch, we'll have to leave 5 instructions blank in the schedule because that will be the time to fill up the instruction buffer again with the destination of the branch. However, what we have done here is we have separated the two components of the branch. The comparison component, as you see here, has been separated from the branch body itself. In other words, the branch outcome, whether it is true or false, is evaluated earlier, and then the branch is taken after a few cycles here, and in between we have filled up useful instructions. So in other words, this branch's comparison part has been moved up over here, and that created slots for filling up useful work over here. So effectively, now we have only 2 delays slots after this particular branch executes, because the comparison is already known over here, and all this instruction needs to do is, after the branch target is computed, it needs to just carry out the jump. Remember that in other cases, when the comparison was here, we had to leave some extra cycles for computing those over here, and since that has already been done, we don't need to effect the branch after those many cycles, and therefore we have only 2 delay slots over here. In other words, branch being a complex instruction, what we have done here is broken it down into 2 parts, evaluated the comparison part, filled up with the useful work, then put the branch itself, and now we have lesser number of delay slots because a lot of branches already executed earlier, and we have less wasted work here of only 2 slots. Now let us look at the most optimal form of unbundling, what we call as 3-step branching. In 3-step branching, we also decouple the address computation from the branch in addition to the decoupling of comparison. That result of the target of the branch is now pre-computed and is stored into what is called as the branch target register. The branch target register also stores the outcome of the comparison. Typically, 1 bit is reserved for noting the outcome, and the rest of the bits are reserved for the target address. And therefore, the comparison part and the address computation part are decoupled, and the compiler can move that around in any order. The compiler can therefore schedule it at an earlier point, and the number of delay slots that we have to leave after the branch jumps now are further reduced. Continuing the same example here, now let us take a look at 3-step branches. Remember, in the previous example, we had unbundled the comparison part of the branch and we executed it ahead of time. Therefore, the branch instruction was simplified and we had 2 delay slots sitting after the branch. Now in this 3-step branch, in addition, what we have done is we have computed the branch target also ahead of time, and the first instruction does the comparison, the second one does the target. Then we fill it up with some useful operations. And then finally the branch executes over here corresponding to this simple branch instruction, which is going to use the results which are pre-computed in these 2 registers. And therefore, since the work of this particular instruction is much lesser now, there's only 1 delay slot, as you can see here, as against 2 delay slots in the 2-step branching. So in 3-step branching, because we have taken out the work that is done in the branch and could get it done ahead of time, we are able to move those operations earlier. The compiler does these things, and we can fill up in between operations with some other instructions, and we have only 1 delay slot finally to worry about for a branch. And therefore, this type of unbundling is very, very efficient in terms of having to worry about the least amount of delay slot over here. You might wonder why the delay slot is so minimal here. You can see that the branch target is also known at this particular point, and so is the condition. So we can start fetching the instruction stream which is at the right destination and keep it ready. Therefore, once we take the jump, we have minimal work to do to just transfer the control to that particular PC address. And that is why the delay slots here is just 1, unlike 5 delay slots earlier. So you can see that the goals of optimizations are keep the branch target ready or the PC address ready, and keep the condition ready to select the right target, and then start processing and fetching those instructions, and therefore minimize the delays once the branch actually jumps. So you may wonder that if this is the case, 2-step and 3-step branching should be very commonplace and is an obvious solution to the latency and the delay problem in terms of branches, especially in VLIWs. What's the catch here? The biggest problem of these is the increase in code size. Why it is so? As you can see in those examples that we saw, additional instructions are generated for each of those solutions. 1 additional instruction is generated for 2-step solution, and in fact 2 additional instructions are generated for 3-step solution. So assuming a frequency of 1 branch for every 7 operations, which is quite typical, in 2-step branches we typically have a code growth of 14%. Even worse, for 3-step we have 28% code growth. 14% code growth is somewhat tolerable, and therefore 2-step solution is quite commonly adopted in embedded CPUs. But 3-step solution is rarely adopted because of a significant code growth of 28%. Now we are going to combine our knowledge of how VLIW instructions operate along with the branches that we just saw. Remember again, each large VLIW instruction consists of sub-instructions that execute in parallel, and then some of them could have a branch so that we transfer the control from the current PC to the destination. So I have here few different statements which assume a clustered VLIW architecture. In other words, we have different register bank and different clusters and different function units so that we support the parallelism as we saw earlier. And we are encountering a branch as an execution, and therefore at that particular point, what do we need to do as far as the different clusters are concerned? Remember, the branch will execute on one of the clusters. So the questions ask you, what is the intended outcome here and what do we need to do in terms of implementing this branch? Please mark your statements as true in the following statements. The first statement is, in a VLIW architecture with unbundled branches, the branch targets must be computed once for all clusters. The second statement is, the branch condition is computed in one cluster and broadcast to all other clusters. The third statement is, if the branch condition is taken, each cluster transfers control to one branch target. And the final one is, all branch targets correspond to the same logical block. Please mark your answers which are true with a tick mark. Go ahead and write your answers now. So let us see the answers now. The first statement is, in a VLIW architecture with clustered register banks, the unbundled branches, the branch targets must be computed once for all clusters. Remember, the keyword here is all. The answer here is, of course, false. The reason is, remember that the branch will execute in one of the clusters, and it cannot be that there are 4 different branches which are parallelly executing. That instruction schedule will never result, and therefore this condition will never arise of computing the branch targets for each of the clusters. The next statement, the branch condition is computed in one cluster and is broadcast to all other clusters. This answer is true. Why is it true? Because in a parallel schedule, there will be only one branch. It will execute in one cluster, but after that branch executes, the next VLIW instruction that we need to compute will reside at its destination or the branch target, and therefore all the clusters need to be notified in terms of the branch condition, and therefore it is broadcast to all the clusters. This statement is also false because the other clusters don't have even branch targets because they do not have any branch instructions. They need to be simply notified which is the next PC address we are going to execute, and therefore they do not affect the transfer of control because they do not execute the branch instruction. Again, this is due to the fact that in a VLIW program, in a given bundle, we'll have exactly one branch instructions, and the other ones will be other operations which are non-branch. Finally, the last statement, all branch targets correspond to the same logical block. This statement is correct because finally we are going to start executing into the next block which is going to be affected by that particular branch instruction, and therefore the branch targets correspond to the exact same logical block. So this gives us a subtle idea of what is exactly the difference between affecting a branch, going to a logical block, versus a branch target. Remember again that in a VLIW setting, and keeping things very simple here, so this could be a branch instruction, and that could be, for example, an add instruction. So after we execute add, we need to go to the exact same logical block as it's shown over in the last things, and it needs to be notified that go to that particular logic block, and therefore this one computes the branch condition and is broadcasts it to all the clusters, such as the one which is executing add, asking it to implement going to the next logical block. Now all the previous discussion was corresponding to a single branch being present in a VLIW bundle. But remember, VLIW has parallelism. So what else we can do with it? Some very advanced VLIWs support what we call as multi-way branches. What are multi-way branches? We'll look through an example a little later, but a multi-way branch allows us to go to multiple destinations using a single execution. Multi-way branches are implemented for higher ILP, and in fact to implement a sequence of if-then-else conditions which are nested together. Multi-way branching needs to be implemented in a very cautious manner. What it needs to implement is the original sequential program semantics. Branches must be prioritized, and execution order must be carefully preserved during bundling in one VLIW instruction. Let us take a look at a simple nested if-then-else and see how we can implement it. What we have is a very typical occurrence in a program wherein we have a if condition on X. If that happens to be true, we go to destination A. However, if that happens to be false, we evaluate the next branch, which is predicated on Y. If this branch happens to be true, we go to B. However, if it happens to be false, then we go ahead and execute a third branch, which is yet another if which is nested inside, and this condition is on Z. If that happens to be true, we go to destination C. However, if Z is false, then we go to destination D. So you can see here is a sequence of such branches, and this will completely abolish all the benefits of VLIW if we allow only one branch per bundle, or in other words, in each of the VLIW instructions, if we just allow one branch, then we'll have to put these branches one after the other. There will be delays there, and the execution will be significantly slower because of the delay slots, because one branch depends on the other, and so on. In general, such a chain of branches also results many times not at the program level, but at the compiler level. The main reason being, if a particular branch cannot span a large jump, then it is broken down into different pieces which chain after one another, and that leads to multiple chain of such branches. Of course, in this particular case, this chain of branches is again due to a nested if condition, which is typical in many programs, and these are conditional branches which are chained together. Let us look at its implementation in a multi-way branch VLIW. So let us start how this is implemented in a bundled VLIW sense. First and foremost, if all the conditions are false, that is, if X is false, Y is false, and Z is false, we simply do not execute any of these branches, and we just fall through and execute the next instruction, which is at D. And that's shown over here. Typically, all the branches being false, we do not carry out any jump whatsoever, and we fall through and execute an instruction which is at target D. That's shown over here. Now, in terms of the VLIW execution, here is how it works. The predicate of the second branch depends on the outcome of the first branch. So if the first branch happens to be true, the predicate of the second branch and third branch happens to be false, and the effective destination is A in this particular case. However, if the first branch is false, then the second one gets activated in terms of its destination. If that happens to be true, then the destination of this branch will be B, and the outcome of the second branch will decide the predicate for the third branch. If the outcome of the second branch is true, then the predicate for the third branch is false, and therefore its destination is discarded. However, if the predicate for the second branch happens to be false, that in turn activates the branch 3, and its target becomes the effective target of the branch, which is C. So as you can see here, if all three are false, then none of the targets are active and the instruction falls through. However, if first is true, then that is effectively the target of the branch, and it effectively turns off the other two outcomes because their predicates, as decided by the first one, are false. If, however, first one is false, second one is true, then the destination becomes B, and the outcome of third branch is nullified or is turned off because the predicate is decided by second one, which is set to false for the third branch. And then finally, if both first and second are false, the third branch will commit and will go to destination C. So multi-way branches are very complex, as you can see, because those predicates and their destination targets and other things have to be carefully managed for sequential semantics. Now their implementation has to be considered again in clustered VLIW architectures. So the question is, how can we efficiently manage the branch conditions and targets for multi-way branches across multiple clusters? The solution was adopted in one of the architectures called multi-flow trace. So multiple branches per cycles were okay. In other words, to implement multi-way branches, we had multiple branches per cycle, but each cluster had its own branch unit using local condition and target. So in other words, the branch was completely independently computed in terms of its condition and target. And then finally, in order to select the final destination of the resulting branch, a global controller was implemented, which was using predication. As shown in the previous example, the outcome of the first branch is used for turning on or off the outcomes of the remaining branches. and in a similar way the outcome of the second branch, if it was turned on, was used for turning on and off the subsequent branches, the third and fourth and so on. And in this particular way, using predication, one of the branch targets was activated to be the destination PC, and therefore the branch jumped there as a VLIW instruction. You can see that predication had to be implemented here across different clusters, and that implements what is the destination PC here. Now this can cost overheads and slow down the clock, but it also has a benefit that multiple branches now are not sequentialized and are able to implement using a multi-way branch, significantly getting rid of all those delay slots and sequentialization of those branches. Such a solution is very useful when we have an extremely branchy code. Many times case statements are implemented as a sequence of if then else, and so if we have lots and lots of case statements, this solution will also be very efficient. Some multi-cluster solutions involve computing the branch target address in one cluster and leave the implementation of the branch comparisons individually to the cluster. What is the benefit of this approach? The benefit of this approach is many times the target computation is kind of complex, and therefore it is best to confine all the target computation operations to one cluster, making that much more heavy, and leave the other clusters simple to compute the branch conditions. Here is an example of such a solution. As you can see here, there are multiple targets which are being computed inside the cluster 0, and then different clusters, cluster 1, cluster 2, cluster 3, they are computing their individual branch conditions. Those conditions are being fed here, and then using predication and using the different targets, the next destination of the branch, which is the next PC at which we will start executing, is selected. Again, as you can see, predication will be implemented by using these outcomes which are fed to this particular unit. The code which is generated by the compiler looks something like this. Each of the clusters implement the branch comparisons. The branch itself, in terms of its target, is left to the cluster 0 with different destination addresses L0, L1, which are computed, and then using the outcomes which are coming from cluster 1 and cluster 2 and 3, the particular destination is selected over here. So let us test our knowledge of how we understand the multi-way branches using a simple program. So what we have here is a program consisting of some loads and some branches which are sitting here in this simple schedule. And we have multiple branches. Either we take this branch and leave this control flow, or we go through here and we evaluate the next one. Again, depending on whether it is true or false, we go this way or we go that way. Finally, we do the same thing over here, go down or go out. And then finally, we do the same thing in the last unit. And what I'm asking you to do here is put these instructions over here in the schedule, mark these letters as A, B, C, D up to H into these respective blocks to show where we are going to undertake the multi-way branch. So please go ahead and write your responses over here in terms of how this program will get implemented through a multi-way branch, and put those letters in these different boxes. As you can see here, the answers now are: first box, we have a load here. It's not a branch, so we are going to put all the instructions which are definitely going to execute over here. The first one will be this load, which is the instruction at location A. The next will be, of course, this another load, which is the instruction at location B. And then the third one again will be that load which is going to execute, which is really not a branch, which is going to execute in location C. So those are the three instructions that are going to execute. From this point onwards, as you can see, we start taking the branch either this way or go this way, and similarly this way or go this way, and so on. So all these 4 branches that we have here, including this, we are going to now implement as multi-way branches using these boxes. So let's see the next level of solution here. The next thing that we are going to do is now start evaluating the branch conditions. Remember, the branch conditions and the branch itself are two different things and are unbundled here. So the next condition that we are going to check is this E, which is check R7 rec 1. So that's the next condition that we are going to execute here. Similarly, the other branch condition that we are going to do over here will be this one which sits at G, check R8, and we are going to evaluate both of these branch conditions here. You can see that a bundle of the branch conditions is created over here. Similarly, earlier a bundle with all these loads was created here. And next, we are going to actually start checking the branches using those conditions. So the next one to do here is this branch which is at D. Then there will be a branch which is at F. And finally, we have a branch which is sitting at H. So in other words, what is going on is we first evaluate the branch conditions here, or the comparison part of the branches, and then based on the outcomes that we had, we implement a multi-way branch consisting of D, F and H at this particular point. The way it will work is, if D happens to be true, then we are going to take this particular path and leave. If it happens to be false, we are going to go through here, and that in turn is going to activate the F. Again, the F's condition would have been known earlier, and depending on whether it is true or false, if F happens to be true, it is going to go this way. If it happens to be false, it's going to activate H and go here. And again, depending on H's condition, we are going to go this way, or we would have gone some other way. So in this way, we have D, F and H implementing again a multi-way branch as we talked in the previous slides. And we have separated the branch comparisons, and we have completely separated the load stores which had nothing to do with the branches and bundled those together. Remember, the branch predicates are getting generated in this multi-way branches depending on the comparisons, and they are turning on or off the commit of that branch, and only one of the branch will get selected in terms of going to its target, and the other ones will get deactivated, and that will be a result of the predication. So students, having discussed the multi-way branches, which are really important for implementing a chain of if-then-else's, many case statements are also converted into such a chain, and in order to efficiently implement it, we saw how VLIWs allow you to do this as a part of the bundle. Now let's switch our attention to the next topic in terms of what are the other kinds of branches that are present over here. As you know, we have lots of branches due to loops. And so what kind of branches exist inside those loops? Of course, there are conditional branches which will exit when a certain condition is fulfilled, such as the while loop terminates or repeat until terminates and so on. But more importantly, we also have unconditional branches which go back to the beginning of the loop and iterate the loop for the next iteration. To support such branches, we have what is called as zero overhead looping. So what we have here is special instructions called loop start and loop end, which keep track of the PC address where the boundaries of the loops are, and then the branches are automatically scheduled, which are unconditional branches, from the loop end to loop start, and they have zero overhead. In other words, the hardware schedules these branches appropriately so that we don't pay any bubble penalty there. These kinds of branches are very popular in DSPs. They're also used in some general purpose machines, such as in IPFs. We have not only such branches, but we also have special register called loop count register and branch top operations. What are these? In addition to the unconditional branches, remember that in every loop, we have to keep track of the iterations and the condition. And when the condition is met, we terminate the loop. So loop count registers keep track of those conditions, and branch top operations allow you to terminate and exit the loop, especially in while loop. In PowerPC, on the other hand, we have link and count registers, which keep track of these things. And the linkage is towards where the branch executes, whether the branch is terminating the loop and linking to the PC address outside the loop, or whether it is simply getting nullified and continuing through a fall through and continuing the next iteration. So again, for implementing branches within the loops, we have special instructions, we have special scheduling of those branches by the hardware for unconditional branches, and for conditional branches we have special registers and the branch linking to exit the loop or continue the loop within the body. So having seen these different branches, multi-way, the ones which are inside the loop and so on, now let's turn our attention again to the fundamental ways in which we address the latency issues or the bubble issues in the branches through two different mechanisms. One is speculation and the second is predication. Recall, what is a speculation? We ignore the branch and we bet on a particular direction and we start executing those operations. If we mispredict, we'll have to recover, throw away certain results and redo those operations. So there is a penalty associated with it. Predication means try to execute all different sides of the branch and then at the point of committing the results, decide on the branch outcome or use the branch outcome, pick one set of results which are on where the branch is taken and commit those results, ignore the rest. So now let us discuss the speculation in depth. There are two types of speculations. One is, it is done through software. It is very fundamental in VLIWs and the compilers implement it because again the schedule is under the control of compilers. So speculation means scheduling these operations early on and therefore those are done by the compilers. Hardware speculation is prevalent on the other hand in superscalers because the scheduling is under the control of the hardware. So one of the key aspects of speculation is how to possibly execute the code ahead of time. So regardless of the scheme, whether it is hardware or software based, the techniques are always conservative. That means you don't move the code to a particular place which is early on and leave it there without compensating for it unless the legality of reordering is proven. In other words, imagine a load operation which is sitting on both sides of the branches. Now we can try moving it up all the way before the branch. In this case, we are able to move the load at an earlier place over the branch. The reason is, regardless of the outcome of the branch, we are going to execute the exact same load on either side of the branch and therefore such a reordering is legal. As against this, imagine a speculative technique. So imagine this load being sitting on one side of the branch but not in the others. So when the branch takes place in one direction, we will execute this load. On the other side, we will of course not execute the load. So in a speculative execution, we will execute this particular load betting on the fact that the branch goes in that particular direction which has a load on it, and that therefore speculation is based on probabilistic assumptions. Now, what if the speculation is wrong? Well, we got to make sure that if we execute that load and the branch goes in the other direction which does not have the load, then the speculation was wrong and we must correct it in some particular way. We can probably undo the result of this speculation by reloading the old value into that register and keeping it there for execution. So that is one way to correct the speculation. So what is the biggest benefit of speculation? The biggest benefit of speculation is because we are executing things ahead of time, we can tolerate long latencies. For example, if the load takes long time, because we started doing it early, by the time we need the result of this load, the data is already available. This in turn is going to increase our instruction level parallelism. But what is the flip side to doing this? Well, the flip side to doing this is two things. One is there is a register pressure. Now we have started doing this load earlier, so we need a register much earlier than where we needed it otherwise. And so the demand for registers has gone up here, and so is the register pressure. The second important implication is the complexity. What if the memory operations come back with an exception? Remember, at the original place of the load, we could have created this exception. Now we are going to create this exception early on. And in that case, what happens to all the instructions which are sitting there, waiting to be executed? How do we propagate this exception, or whether we propagate this exception onto those instructions? That becomes a question, and so the exception handling becomes a complex affair. So now let's do this speculation for two different mechanisms. The first mechanism is speculating on the control flow or execution, called control speculation. So what does control speculation really means? Control speculation deals with moving an instruction above a branch. Like we discussed in the previous slide, a load would be moved at an earlier position and would start executing, anticipating that the branch is going to take that direction which has a load. So in that sense, it removes the control dependence of this load on this branch. And what is the implication here? It is about latency hiding, and it improves the ILP because the stalls are reduced because of this mechanism. Having seen the benefit of speculation, now let's look at an important part of how to deal with exceptions. So the real question is how to correctly report and deal with these exception conditions. Now let us classify the effect of these exceptions on two different types of instructions. Integer arithmetic operations are always safe. In other words, if we don't receive a proper value, we can easily undo those operations and claim that those different operations are to be redone. But memory references may also throw an exception. So for example, a load might generate an exception, and the question is how to deal with those exceptions. So there are two choices for handling exceptions generated by mispredicted operations, and those exceptions are generated at an earlier point because these operations are moved earlier, and we'll take a look at these two different mechanisms now. So the first model is non-recovery speculation model. In this model, we only signal errors and discard certain operations, but do not recover or correct this exception. So we classify the set of instructions into two categories: silent instructions, which simply ignore the non-recoverable exception that is triggered here. And what is the outcome of this exception then? Those instructions are simply cancelled which cause the exception, and other instructions simply ignore those. For example, dismissible loads. If sec fault occurs during those operations, the load itself is simply cancelled. This model is adopted because recoverable exceptions such as page fault can be expensive, and many times the embedded systems especially do not have the necessary hardware complexity to deal with these exceptions. Now you can see that the non-recovery model, although it is simple and simply involves raising an alarm, an error or a signal and throwing away the instruction, it also has limitation that it is not useful for precise exception. What is a precise exception? A precise exception also tells the effect on the instructions which are affected by the instruction, and in this model this effect is not shown. But in embedded systems, what is the real goal of an exception? The real goal of an exception is to signal errors, and the operating system then takes over the control of the program and maybe causes a termination or gives some major feedback to the user, and most likely does not result in anything else. And so this is sufficient enough. So non-recoverable speculation model is sufficient enough for embedded systems because of this reason. For example, if a load generates a memory error, we don't need to worry about the dependent instructions on that load, but an error is simply given to the OS causing the memory fault. The memory is then examined by the OS, and a sec fault is treated as a termination of the program. So in short, there is no need to propagate this to the dependent instructions, and that's why non-recovery model is good enough. Let us understand the issue of recovery-oriented exception processing as far as the control speculation is concerned through a simple example. Here, what we have is the original code. As you can see here, there is a branch, and following that branch there is a whole bunch of operations here which are loads on R1 and R3, and using the results of R1 and R3 some new registers are being computed here through add operations. For example, R4 is equal to R3 plus 2 through an add operation, and R5 is R1 plus 3 through an add operation. Finally, what we have here is a store using the value of R4, which is stored in the memory on an offset which is given by R2 and 4. So in short, this code executes only after the branch, and depending on the outcome of the branch, if it is fall through, this particular code executes. If the branch takes us somewhere else at L1, this code will definitely not execute. As you can see, for this code, if it does execute when the branch falls through, which might be the common case here, we'll pay significant latency for these two loads before the adds which are dependent on them can execute. And in order to hide this latency and the delay, what we decide to do is speculate that the branch will fall through and move these loads up over here. So in the speculative code now, what we have is, we have all these operations which were loads earlier moved above the branch. So we have the load operation moved above the branch here, which was originally after the branch. It is now moved before the branch. Similarly, we have a dependent operation which is also moved above the branch here. We also have the other load moved above the branch, and then we have an add operation which uses these values moved also outside or above the branch. So all this executes speculatively. What we also have is what is called as a sentinel, which is going to check if the speculative load, for example, has executed and the value which is generated from it is right or not, using this check instruction. Similarly, there is another check instruction which is a sentinel, which is set up here to make sure that the speculative loads are executed and the value of R4 is computed properly. What if these checks fail? If these checks fail, then the chain of instructions on which R5 was dependent has to be re-executed, and so here is the recovery block that is kept by the hardware. R5 depends on R1, and R1 is the speculative load. So what we'll do here, in case this check fails on R5, we'll go ahead and execute the speculative load again, get the right value in R1, and we'll compute the addition and we'll generate R5 over here. Similar is the case for R4. We'll take again those instructions on which R4 is dependent. We'll take those, such as this load on R3, we'll re-execute it, then we'll re-execute the instruction which uses that value and regenerate that value and make it ready over here. So in short, what we have here are recovery blocks which are sitting there to make sure that the exception, in case it happens, is processed and the right values are set up over here. These recovery blocks, of course, do not execute under non-accepting part. The control flow simply keeps going straight down, and if the checks are passed, it keeps falling through and reaches this particular point. However, if one of the checks fails, it invokes the recovery part, and once the recovery is done, we come back here and start executing over here. So for example, if the checks fail on R5, we'll go here, re-execute this, the control flow will come back here and we'll resume the execution. If the check on R4 is also failing, then we'll go here, we will execute the recovery block and come over here. However, if the checks are all correct, there is no exception, we'll just keep going down. So you can see that the common case when the checks do not fail is simply a straight line execution which is executing as though nothing has happened. Now let us turn our attention to another important part of speculation called as data speculation. So what is going on in data speculation? Remember, data speculation is mainly used for making sure that the current value of data that I have loaded from memory is in fact the right value. So imagine a store that is going to a piece of memory and a load that is going to another piece of memory. Now let this be storing a value through a particular address, through a pointer, and let this be loading a value through another pointer from the memory. Now we don't know whether these two pointers are going to point to exact same memory location or not. Now what we try to do here is speculatively move the load above the store to start getting the value from the memory ahead of time. Now remember, this is the memory which is the store's memory, and this is the memory which is load's memory. If these two happen to be two distinct pieces of memory where the pointers are pointing to, we are good. We speculatively get a value from this particular memory over here, and subsequently a store is writing a value to a different piece of memory over here. But what if the two are the same? Then the value that we have loaded earlier is a wrong value, because first the store is supposed to store a new value over here from which we are supposed to load, and that's a question of misspeculation. So in short, the earlier example showed us how to schedule a load ahead of a store, and with a hope that the loads and stores are going to two different addresses, and so that we can start loading the value ahead of time. We need, of course, a check whether the load and stores have turned out to hit the same memory, and therefore it's a question of misspeculation, and we'll have to recover from this action. How do we do that? We can just re-execute the load, and now it will see the right value in the memory, and it will get the right value from the memory. So in this case, the recovery is important because we have to have the right value in the register, and even if we had the load started early and got an old value, and the store subsequently stored the correct value in that memory location, the recovery can be as simple as just re-executing that load and getting the new value which was put in there by the store. So due to its simplicity and utility, this particular mechanism can hide the latency of the load operation. Let us understand how we can do some of this data speculation, disambiguation through a series of instructions in software. Earlier I mentioned to you a hardware mechanism of just simply re-executing the load, but of course it does cost additional mechanisms to be implemented in hardware, and embedded systems may not have a provision for such correction. So an alternative is given many times to an embedded system designer to put some software instructions and the memory disambiguation to be implemented via software route. What we have here is an original code in which again we have a store to a particular memory here. What it is doing is taking the value of R1 and storing it into this memory. The base address is given by R7 and the offset is 8. Subsequently, we have a load instruction which is loading the value from yet another piece of memory where the base address is given in R5 with the offset of 16, and that value is being loaded into register R4. The original value R1 is computed by a multiply instruction which is sitting here, and that sends it to store, that stores it. And then finally the loaded value R4 is being used in an add operation which is sitting over here. So the way the code executes in a non-speculative manner is as follows. As you can see here again, the problem is the load will take more cycles, and because of which the add instructions can get stalled. So in a speculative version, the load is moved above the store, and in this particular case, we are allowed to move it at the earliest place over here. So the load starts executing speculatively here. Following that, we do have the multiply operation. And then finally, we have the store operation, which takes the value of R1 and stores it into this particular memory address. Now, one big question that needs to be answered is, what if in the original code, the store wrote into exact same piece of memory over here. So this store went ahead and wrote the data in this piece of memory, and this load read this data exactly from the same piece of memory. Under such a situation, this execution of load before the store would read a wrong value because the store would not have had an opportunity to put this value, and the load will read a stale value here and the program semantics will be incorrect. The real question is, how do we detect that the load and store exactly point to the same piece of memory and the same location? We do not have a way of detecting this in the hardware because lack of hardware. So what we could do is we could generate a code which is able to detect it. It is very simple how we detect. In fact, these two locations are pointing to the same exact memory by simply keeping track of those actual addresses through a simple instruction. So this is the way the two addresses are being compared in this particular case. This is the base address R7. This is the offset. So the addition of R7 plus 8 is being compared with R5 and 16. If these two happen to be equal, then we have a problem. So the same equation is being rearranged here in terms of this code. We are taking a difference here between R7 and R5, holding it over here in R10. And then the relative offset between 16 and 8 is being used here to be added to this R10. And we are holding this as a branch condition of comparable equal to. So in case these happen to be equal, the B1 bit will be set here. And then we have finally a comparison operation here. If the B1 bit is set, then we are going to copy the value of register R1 into R4. Why is that? Because under that situation, the right value would be sitting in R1 here, as you can see, which was used for carrying out the store. And a wrong value will be, or an old value will be sitting in R4. So all we are trying to do here is trying to implement this particular operation of transferring the right value which is sitting in R1 into R4 in case the addresses are colliding. So that is accomplished by this particular instruction here. And so eventually we have the right value resident in R4. So students, now let us take a quiz on speculation. We haven't done a quiz for a long time. Let us make sure we understand speculation properly, especially control and data speculation. So let me describe what is going on over here. So we have these non-speculative instructions, div and add sitting here. And what we would like to do is convert this particular program, because div is going to take a long time to execute in the hardware. It's going to have a large amount of latency, just like a load has. It's a floating point division. And therefore it is going to delay this add instruction, creating stalls. So we would like to move this div instruction earlier, and the way it is going to work is, if an exception occurs during division, you might ask yourself a question, why would this exception occur? And I would let you think a little bit about it. And remember, this is a div instruction, and there could be a division by 0, for example, over here. So if an exception occurs, then it will be propagated to the result, and the other non-speculative instruction which depends on it, seeing this exception, will also be discarded. That is the semantics of this. Now, the speculative version of div is called div e, with an e added to it in our case. And so fill in this particular program on the right hand side by using speculation here, and go ahead and write your answers, which instruction sits where in this control flow graph on the right hand side. The correct answer is the div instruction converts finally from div to div e, because that is a speculative instruction. Not only it changes to div e, but is also moved up, as you can see, into a earlier point over here, and it starts executing. And then the add remains where it is in a non-speculative way. And what this does is it creates enough amount of gap between these two instructions so that the result is available in V1 and add is not stalled because of that. The way this would work in terms of exception is if there is a division by 0 error there or an exception, V1 would carry that exception over here, and all the instructions which depend on V1 where the result is erroneous would get affected and would get tossed out. So in other words, this instruction will also get discarded because of that execution, and what we may have to do is, of course, take further actions of propagating this exception and maybe halting the program and so on, but that is in the realm of operating systems. We just want to make sure that all the instructions are discarded and no results are put into the memory which are bad. Let us consider now the next thing that we have been talking about. Having seen speculation, now let's look at another mechanism which is called as predication. What is the goal of predication? The goal of predication is to be able to convert the control flow into a data flow, executing both sides of the branch and then committing only one side of it to the memory. So what we have here is a simple program which is testing the condition on X. If the condition is true, it does A star B and puts it into C. The condition is false, takes the value of C and puts it into an array. So this is resulting in this type of assembly instructions. We have a comparison here, and then we have a branch which is going on the outcome. When the outcome is true, we are going to do these instructions over here. When the outcome is false, the branch is going to go here and it is going to execute the store which is corresponding to this P0 equal to C. So again, our intent here is to convert this program into a predicated version, but trying to execute both sides of the branch as though they're just as good, and then finally picking one version and committing it to the memory. And that's how we convert the control dependence to a data dependence. We'll look at how this conversion happens in the next couple of slides. So the first mechanism that we are going to look at is called as full predication. What it does is executes all individual operations on both sides of the paths or the branch, and then uses the condition to decide which path is to be thrown away and which path is going to be committed to the memory. So again, let's take a look at the same exact program, and what we are doing here is comparing this branch and holding the result in P1 over here. But notice now that we are using that P1 to tag an instruction over here, which is the true side of this particular branch. And if P1 is true, the MPY will execute normally. In short, if P1 is false, the MPI will become a no-op and its result will not get committed to the memory. So you can see that this particular solution needs, of course, a special predicate register such as P1, and then not only we need that register, but we need predicate defining or predicate tagged instructions such as these. Remember, this is a different instruction which has been tagged by this predicate register, and depending on the predicate register, either this instruction will be committed or will get thrown out. So a different mechanism here is partial predication. What is the difference between full predication and partial predication? Remember that in the previous slide we looked at full predication, in which we had a tag associated with an instruction and the commit of that instruction was dependent on the tag. The difference here is, in partial predication, we are going to execute all individual operations on both sides of the branch, and then we are going to select the final one based on the condition. So we'll have both sides of the branch executing, both results being available, and finally this is the part which is going to decide which is the result which we are going to actually use and discard the other one. So here is the same again program which is now rewritten in this particular way to use partial predication. We do have the same multiply operation here. We do have the compare instruction into B1, and then finally we are going to select based on the outcome of this branch whether we will use the value of R4 to go to R3 or whether it will remain as R3 based on the outcome. So in other words, if the branch is taken in which we were to execute this multiply that will generate this result R4. Eventually that is the one which will reside in R3, whereas in other case, if we did not take that side of the branch, the original R3 result will remain where it is, and finally we'll have a store which is being done based on that R3. So you can see that the main difference here between the previous one and this one, which is a partial predication, is the use of the condition to decide which result which we'll select out of these two to be put into the destination register over here. You might ask me, based on your knowledge of VEX, why are we using SLCT as the instruction here? This was the most general solution that we have. In this particular case, there is no point reassigning R3 to itself, and so we could alternatively use a C move or a conditional move which uses the result of B1, the condition that is of that branch, and in case the result is true, we are going to move R4 into R3. If it is not, we are not going to do anything, and so we could make a more efficient code generation decision over here. But in general, we would be using SLCT type of an instruction, because we could have, instead of this R3, some other result present in another register, let's say R2, and then it will be a question of whether to assign R4 to R3 or R2 to R3, and that's why this instruction. So we have talked about full and partial predication. However, one of the things that you must understand is, unlike speculation, predication does not reduce the critical path. In other words, it does not improve the latency, because the operations execute where they are, and therefore we do not incur any reduction of the critical path. So when to use speculation is, of course, we want to improve the latency or the critical path, and we could do so by promoting those predicated operations above the branch, such as over here. We could use these predicated operations which are dependent on the branch condition, and we could move these above, and therefore we would be able to reduce the latency there. So then, if the latency is not really beneficiary of predication, what is its benefit? One of the biggest benefit is to use with difficult to predict branches. Now what we are doing is removing a branch and creating linear code which can just sit there with a predicated register attached to it, and so we can create larger blocks of linear code which are called as basic blocks. We are going to talk about these a little bit later when we start discussing the compilers. But these larger blocks allow you to look at large piece of code as a unit, and you can do a lot of optimizations on them. For loop-intensive programs, predication improves the ILP because of better software pipelining, and you can see that because of these large blocks of code, we can move those around between different iterations, and we can create a better schedule. Predication is most effective when balanced paths or the longest path is the most frequently executed path, because we are going to execute both the paths. We don't pay the penalty when the paths are balanced. Or when one of the paths is really long and it's frequently executed, we are going to go and execute that based on the branch outcome without waiting for it. The shorter paths, on the other hand, will take longer time to execute. The main reason for that is now you have to wait on the execution to be facilitated by the predicate register. What is the disadvantage in general of predication? The disadvantage is it complicates the hardware. Now you need the special predicate register. You need a mechanism to commit those results of the different sides of the branch based on the outcome of the result. And finally, you are going to execute a lot of code here which eventually is not going to get committed, and that will add to the resource pressure. And so because of the resource pressure, we will have to add more logic, and the critical path can probably get slowed down, and the clock could go down in terms of its frequency. Remember, the more the complex the hardware is, or the longer the critical path is, the slower is the clock. So let us take a look at how the predication trade-offs are in the embedded domain. First thing is, implementing full predication means pay upfront. What does this mean? This means that you have longer instructions. For example, in IPF, 42 bits encoding size for 6 predicate bits, you have large number of predicate registers, and so on. And so in general, more hardware complexity doesn't sound good for embedded processors, and so this solution is expensive. On the other hand, partial predication, which means the use of a conditional register and an instruction which will take two different results and decide which one to use, is the right way to go because this is a pay-per-use model. The instructions remain simple. There are no special registers. The length of those instructions remain simple as well. Many instructions which do not need predication are not predicated. The only flip side is increasing the code size, because now we have to have those select operations such as SCLT or CMove being present in the code. Because of this pay-per-use model, instruction simplicity, and moreover hardware simplicity, this model of partial predication is useful and is appealing for embedded processors. Now, having understood predication, it's time for a quiz. Select all the statements that are true from the following list, and when a statement is true, put a check mark against it. Here are the statements which I'm going to read out. The first statement is, does not allow the compiler to overlap the execution of independent control structures without code explosion. Is this statement true for predication? The second statement is, allows compiler to reduce the frequency of branch instructions and consequently of branch mispredictions. In the presence of predication, is this statement true or false? The third statement is, increases the number of branches to be tested in a given cycle. Is this true or false? Finally, the next statement is, increases the number of multiple execution paths and associated hardware costs, copies of register maps, etc. And finally, the last statement is, allows code movement in superblocks. Please go ahead and mark all the correct statements by putting a check mark against them. Now let's take a look at these answers. The first statement, predication does not allow a compiler to overlap the execution of independent control constructs without code explosions. This statement is false. So as far as all those instructions which are independent, the compiler still is able to schedule them efficiently, and predication does not hinder that at all. Let's look at the next statement. Allows compiler to reduce the frequency of branch instructions and consequently of branch mispredictions. This statement is true, and so the conversion of control dependency into data dependency allows you to execute both sides of branch and gets around the branch penalty. Let's take a look at the next sentence. Increases the number of branches to be tested in a given cycle. The predication is removing those branch conditions, and therefore this statement is false. It in fact decreases or gets around or eliminates all the branch conditions. The next statement is false. Why? Because we are able to now use the execution on all the paths, and the hardware costs are higher in full predication. The partial predication also allows you to execute multiple paths, but the hardware costs are not increased because of the conditional move kind of instructions. And finally, the last statement allows code movement in superblocks. What is a superblock? A superblock is much bigger than a given set of instructions. It allows you to increase the length of this to add both the sides of the branch and consider that as one linear code which is predicated over here as shown. This is one type of predicate on this side, true side, and this is another type of predicate which is on the false side. Allows you to create this type of long block, and therefore this statement is correct. Now the last part of this we are going to deal with is system operations. So what is the definition of system operations? All the functions that control system around the CPU, that is, those parts which deal with I/O and peripherals, those are important to be considered as a part of the microarchitecture. So far we have been discussing memory, we have been discussing the pipeline, we have been discussing the branching unit, and so on. So what are the most efficient approaches to deal with the peripherals and memory mapped I/O and so on. Most of them had to do with the control registers. So most of the system operations, such as access to I/O or peripherals, typically go through a special type of memory which is called a reserved memory, and that is mapped to a reserved memory page. These control registers allow one to access this reserved memory, and the access to these registers itself is by simple load store mechanism. So in other words, one could load the base value of a page table, and therefore one gets access to that reserved part of the memory. Again, to diminish the latency, especially that is associated with I/O, we can do a speculative execution here to load these values from the I/O and so on. However, we must protect against the exception conditions there, and we must make sure that the values are right. So all the same issues which are associated with speculation again surface over here. Now in terms of this, we cannot simply undertake non-recoverable speculation. We must have here support for ensuring rollbacks and so on, and that is why this speculation is supported only to a limited extent. Imagine a page being loaded having all the wrong values. The recovery part of this means getting the right values, rolling it back, and copying the old values from somewhere into this page. Some of this could be expensive, and so extreme precautions are taken in terms of what level of speculation you can support here. However, many other kinds of system operations are possible via these control registers, or just apart from accessing the special memory. And these registers allow us to do much more than accessing this reserved memory. They also allow you to do synchronization. For example, two threads can talk to each other and synchronize and wait for each other. Interrupt support. It is quite important to process interrupts, and the control registers play a vital role in making sure that interrupt handlers are invoked and so on. The other job is protection and virtual memory support in terms of getting the right values from right place. And finally, during debugging, they allow you to keep track of certain values which needs to be visible to the debugger. In this lesson, we discussed handling branches in VLIW architectures. We looked at the techniques such as unbundling, speculation, and predication. We are now ready to move on to the next phase of the course. Compilers for embedded systems. Here we come.